My co-author is Dr. Brett Webb, who's not here today, and I'm going to talk about coastal guidance development going on right now in Federal Highway Administration. And you know, we are, even though this is Ohio, and I appreciate the Ohio folks giving me good South Alabama weather, you know, 89 degrees, 80% humidity, thank you. There is a fourth coast in the country, and those people in Ohio know about it. It's the Great Lakes, the unsalted coast, as we call it. So most of you are probably not from Ohio sitting in the room. They're probably all in the next room. So let's move on. The primary takeaways from my talk is just simple, real simple. There is new guidance on coastal engineering that's important for coastal highway and bridge design, and some of it's being presently developed. And your input's requested. I will leave at least 5 minutes, maybe 10 minutes at the end of the talk to have feedback from you to me about what ought to be in the next version of HEC 25. So I mean that. So we're talking about roads and beaches, two of America's great love affairs. You guys are experts in one of these two, and the coastal engineers work more in the second one. And HEC 25 tries to get the two fields back together. The fact is that demand for these roads is increasing at greater rates than other demands because coastal area populations are increasing faster than non-coastal area populations in this country. And millions of us want to live near the beach, and millions more want to get there on vacation. And what's the number one way they get there on vacation is they jump in their car. So it's a unique design environment. The waves, the water levels, the sand transport, the tidal currents, the winds, the soils are all unique to the coastal area. And these are, of course, different sciences you have to deal with in the marine sciences and of bays, wetlands, dunes, and beaches. And so every coastal state has some roads that provide access to the coast, and in this case, evacuation away from the coast in a hurricane. And every coastal state has some roads that provide access along the coast. Most coastal states have some roads that cross coastal estuaries, either at grade or elevated up here, and most coastal states have some roads with tidal bridge crossings. And so that's the framework for what we're talking about here today. So the primary guidance document is HEC 25. It was originally written in 2008, the second edition. It's 246 pages. It's comprehensive guidance for the analysis and the planning and design and operation of coastal highways and bridges. Its target audience is basically you, the hydraulic engineer or the planner, somebody with little experience in coastal engineering facing coastal problems. Secondary audience is then experienced coastal engineers providing assistance to you. So that's who pretty much most people in this room are, the civil engineers, the planners, the hydraulic engineers doing the drainage work in the state. HEC 25 has an 18-page glossary so we can begin to speak the same language, and that's important. And so the glossary might be full of terms that a coastal engineer would go, yeah, but you might go, okay. That's what they call it. It's broken up into 3 parts. And the first part's just the introductory part. It talks about what we mean when we talk about coastal roads and coastal bridges, and also talks about coastal engineering as a specialty area of civil engineering that accounts for the unique wave, tide, and sand movement along the coast. In the United States, most coastal engineers are trained at the master's level. There are a couple undergraduate programs, but few, and a couple of dozen master's level programs around the country, including University of North Florida. I'm not aware of one in this state. At one point, there was a coastal engineer on the faculty at the school not to be named that is housed in this city, but that guy has retired, or that lady moved on. So the Corps of Engineers has kind of the Bible of coastal engineering, but that's focused on their mission, and the DOTs have a slightly different mission. So we'll steal from their technology as we want. A lot of the expertise, of course, in the consulting firms that you deal with, and American Society of Civil Engineers has sort of the umbrella organization for coastal engineering, COPRI, and they have a specialty certification, a diplomate of coastal engineering. So I would encourage you to maybe think about that as a requirement in some of your more complex coastal projects. Think about requiring that for your consultant team. Typical master's degree coastal engineering work in the United States now looks something like this. Probably at least 2 courses in wave mechanics. And then other coastal hydrodynamic modeling, sediments, the design, the engineering components, and now more and more the ecology and the geomorphology and the climate science. I'm gonna step off the reservation here, and what I'm gonna say now is not federal highways, but it's me based on 38 years. If I were to come to your office, my guess is it's the headquarters or maybe a regional or district office of a DOT. If I walked around your hallway and bumped into people at random, I'd probably bump into a geotechnical engineer, a couple structural engineers, a bunch of planners and geometry experts, and probably some scientists, ecologists, and people that keep you dealing with the permit specialists. Would I bump into a coastal engineer in your office? Probably not. I'm not aware of any, correct me if I'm wrong, coastal engineer in a DOT or position, period. I used to know 3 and they've all retired. So, but yet you're doing coastal engineering. So think about that. I know you're constrained on your staff, but maybe you ought to be hiring some coastal engineers. Back on the reservation here. Part 2, actually, of HEC 25 is that basically an introductory graduate course focused on some of the science and a little bit of the engineering related to the important aspects for transportation engineers. Tides, storm surge, water levels, waves. We heard all great pictures of the Great Lakes waves. Who was that? That guy left, I guess, yeah. Great Lakes waves are weird. Really steep, really large, and you don't realize it until you stand there and go, whoa. And of course, hurricane waves on the Atlantic are big too. Coastal sediment processes, how sand moves along the coast. All of that's really geared towards this section, which is where the rubber hits the road for you, and that's your problems, issues and approaches in coastal highway design. And basically, there are 4 chapters now in that section: coastal revetments, what else you could do besides a revetment in roads in areas of receding shorelines, highway overwashing, and coastal bridges. And part of the coastal bridges section includes an appendix which has a method that was referred to for estimating wave loads on bridge decks. It's a simple method, explains the prototype damage we've seen in the United States very well, and it turns out it matches some more recent data by others very well, by GWO and all. So take a look at that. A few years ago, Federal Highways said, let's update this with a volume 2 that focuses specifically on how we ought to be assessing the vulnerability of our coastal transportation infrastructure to extreme events, including climate change. So basically that boils down to quantifying future exposure to sea level rise, storm surge, and wave action. And that's what HEC 25 Volume 2 does. Another 10-page glossary, and it presents 3 of the levels of effort, and we heard about a level 3 study from North Carolina, ranging from the use of available data to original numerical modeling at the level 3 stage. And all 3 of them suggest the inclusion of a trained coastal scientist and engineer in the analysis team. Volume 2 concludes, and I still believe this to be true and powerful, that our coastal transportation infrastructure is highly exposed to extreme events today with today's sea level, and that exposure is only going to increase with rising sea levels and climate change. And fortunately, many of the adaptations required for the climate change are the same things we should be doing to improve our infrastructure resilience today. Okay? We're probably not going to come up with new techniques and new tools. We know what they are. So the point of all this is that we're combining these 2 volumes into one document right now. And at the end of this talk, I want to solicit your advice. This is the last time, well, not really the last time, but for all practical purposes, I'm starting to write this tomorrow, so get your feedback in today. If you want something in HEC 25, if there's something there you'd like to see expanded or that you think is missing. So, 4 areas we know we're going to add on to are these. I'll come back to the first one. There's going to be a dedicated chapter on coastal scour. There's going to be new material on nature-based solutions, and I'll talk a little bit more about that in a few minutes on another Federal Highway Administration research effort. And there'll be more on the adaptation strategies or the engineering approaches to addressing this. The first one is what I'm calling increased flooding due to relative sea level rise. Other people call that nuisance flooding or sunny day flooding or king tide flooding or high tide flooding. And it's become a real problem. And the picture here in the upper right is after teaching in the NHI course in Honolulu, the whole class said, well, let's go down to such and such a bar on the waterfront and have our dinner and go home. So I'm following a native from Honolulu down to the waterfront, and all of a sudden he stops his truck, and I'm following in the rental car, and he turns around and says, oh, I forgot, it's high tide, I don't drive this, I have to take a different way, I don't want to drive through that salt water that's backing up through the storm sewer system at high tide every day. First I'm thinking, what's wrong with these people? But then I realized that pretty much we have the same problem in my city, too, at a particular intersection. Anybody here from Alabama? They know which one it is. AlDOT knows which one it is. And pretty much every coastal city in America is having a place like that because a lot of these areas were filled. That was a wetland. It was filled in a hurry over about 100 years ago. And how did we decide where to stop bringing in the fill? Well, we were dredging and throwing it up, and we're pulling in dirt. At some point, somebody said, that's high enough, it's above the high tide. Well, sea levels crept up since then, and it's no longer above the high tide. And this problem is going to get more serious very rapidly, even with existing sea level rise rates at a lot of our places. So let's look at those. This is an original graphic. This shows 6 places along the eastern and the Gulf Coast, Atlantic and Gulf Coast on actual sea level rise in the last century as measured at the NOAA tide gauges. And they're all creeping up on the East Coast. Creeping up, and the scale there is, on the order of magnitude of 1 or 2 feet, maybe 3 feet in the Galveston example. And the difference between those graphics, is the vertical land movement. Galveston subsiding. And the other higher rates that you may see at Charleston has to do with a little bit of subsidence and a little bit of change in the oceanic current. So there's other things going on besides just the global sea level rise. There's whatever your land mass is doing is number one, and probably 90% of the variation or 95% of the variation to date is related to vertical land movement. But there's also other things. One of the more interesting things is that, the large ice sheets actually affect the global distribution of gravity. And so as the Antarctic ice sheet melts, the relative sea level rise in the northern latitudes in the North Atlantic, the other end of the globe, will be higher than other places. So Boston in the future will be seeing higher sea level rise rates related to the melting of the Antarctic ice sheets on land. So it's interesting and in the water. So that's historic. But every climate science model says the rates are projected to increase off the historic rate. And you're looking at 3 different physical process-based projections of sea level rise, and these are tied to the ocean atmosphere global climate models. And the modeling communities decided to come up with 4 RCPs, and you're looking at 3 of those RCPs in terms of what they refer to in sea level rise. And I'll zoom in on the numbers in a second. The top one being 8.5, the bottom one being 2.6, and the middle one being 4.5. There is another middle scenario that the climate scientists model, and that's 6.0. But interestingly enough, because of the slow reaction of sea level rise, it's no different than 4.5 within a few millimeters. So this is essentially the best available science based on physical processes. And so let's take a look at some of the actual numbers. And I'm going to zoom in on that middle one. And this is from not the IPCC modeling, but COP modeling, which is recognized by the Interagency Council as the best existing one today. because it has some of the ice sheet dynamics in it. And the numbers there show the expected value and the 90% confidence values for the next century. So they're saying it's going to be somewhere, if we follow that RCP, somewhere between 1 and 3 feet, with the expected value being about 2 feet of sea level rise. So, whoa, that's a lot of sea level rise. Because if you look back to 2 graphics ago, the numbers were closer to 8 inches in the last century in most places, maybe 12 with the exception of Galveston and Louisiana. This is the global rate. That means this will be everywhere plus the local changes. So that's going to be huge in and of itself. And so we're going to see a lot more of this nuisance flooding, a lot more in these communities. And it's already a problem. There is other guidance from the interagency panel group published in late 2017, and they're the dash lines. This is probably the most important graphic in the whole talk here because it shows the interagency projections, and they're kind of arbitrary, but they are based on science. So that 8 feet is a scientifically plausible sea level rise in this century if everything falls apart in terms of the ice sheets. But the expected values are down there in the shaded area. That's the same graph I showed before, now with the higher scenarios. So what should we be using for planning? And now I'm going to go off the reservation again here, and this is my recommendation to all my clients. And this is not federal highway policy, but it should be. The blue bar is COP, and you can see where it lies with the interagency stuff. So that's what the climate models expect, and it can be higher. So for planning numbers, I think you should be looking at these higher ranges. How would your facility fare if we are at one of these higher ranges? Because nobody's talking about sea level falling. It's going to get there anyway. But for design recommendations, I'm still sticking with that blue line. And if you have a critical facility, a very expensive facility that's going to fall down, if you're wrong, then yeah, you ought to raise it. Maybe look at the upper part of the gray bar or even something higher. But a lot of people are saying, well, we're not going to pay attention to it because it's small, and I'm not accepting that anymore. I don't think that's wise. We ought to at least, that's kind of my floor recommendation, the blue line. If that's what the climate scientists say is the expected value, we ought to take it. It's the best available science, and we ought to be using that as a bottom floor for our design. So I'll go back on the reservation here and move on, because there's 2 other things I want to talk about that are going on besides that. And that's, one is this primer that was released. How many of you have seen this primer on coastal modeling? Federal Highway Administration released it this month. So it's a really well-written document. I didn't write it. My colleague Brett Webb did. And he wrote it for you, a non-technical audience, to understand coastal modeling, at least in the terms of what are numerical models, what inputs needed in a coastal model, how you evaluate the output. And there's actually some pretty high-level discussions of model skill and how to apply them in different levels of analyses. The primary audience is you, to give a broad understanding. That's the term primer. It doesn't tell you how to do the modeling yourself, but it tells you, hopefully, when you're done reading this, you'll understand, how to, when to solicit the expertise of a coastal modeler and what the difference between a coastal modeler and just a coastal engineer is, and be able to determine your scopes of work, and you prepare your request for professional services and communicate with your consultants and evaluate their results in your project. So I encourage you to go read it because it is really a neat paper. Another thing that's really neat is the last thing I want to talk about, and that is an ongoing project on nature-based solutions. Tina Hodges at Federal Highway Administration is the lead on this, and what we're talking about are approaches which mimic the characteristics of natural features like dunes, wetlands, mangrove swamps, whatever is your natural feature that you can use, but they're created by human design, engineering, and construction. And there's been it's an ongoing effort. There was a white paper written about at the beginning of the year, And there's been a series of 4 workshops around the country, and some of you have participated in them, and we thank you. And now we're developing an implementation guide, and you can follow what's going on the Federal Highway Administration website that looks like this. You search for FHWA green infrastructure, and this will pop up. So I've covered a lot of material. The main one is the HEC 25 rewrite that's ongoing, but I also mentioned the coastal primer, and I'll mention the ongoing work on the nature-based solutions for coastal highway situations. And so now I'm done, and I want you. What should I be putting, what should Federal Highways be putting in HEC 25, the next edition?
I'm from California, and they are really pushing managed retreat as a coastal practice. So I think it'd be really good to have some discussion in the engineering guidance on what that means, not only for planning new structures, but the existing structures as well.
Okay, thank you. That is a real option, always. Always. Anybody else? Raf?
You know what I'm going to say. I think your method and the Shepherd method for wave loading on bridges, they're definitely positives. It's a good first cut. I think in future editions we need to be able to do more or have the ability to do better. You know, it's written right now. It's kind of maybe highlight those limitations of those methods a little bit more.
Yeah. At this point in time, what I'm thinking of doing, and we can talk about it offline, is taking GWO's recommendations, because GWO looked at my model, looked at his lab data and said, hey, the coefficients would be better if you set them this way. And it all makes sense to me. So at this point in time, that at least is getting in there.
Sure.
The new recommendations for the Federal Highway Administration method.
On the definitions front, this sea level rise definition needs to be clarified, I think. The fact that there's rebound in some parts of the world and there's subsidence in other parts of the world is not communicated. And so if there was a way to bring that up in the manual and maybe propose a new terminology, relative sea level rise or something like that, it would help.
That's an excellent point. I kind of blow through it real quickly. I won't invent new terms because they're already there. Relative sea level rise. And that's really the powerful thing about the interagency stuff by SWEET is I showed you the global sea level rise scenarios that they're suggesting be used in planning. But along with that, that's the global numbers. But they also have the relative numbers at your location everywhere in a table that you can go dig out that correspond with those. So if the global rate is that intermediate low and you want to assume that, then say you're in Galveston, Texas, you look up in their table for the intermediate low, it won't be 2 feet, it'll be 3.5 feet because of our vertical land movement and these other things going on with the ice sheets. So yeah, relative sea, I will, thank you, I'll emphasize that a little bit better. Because every projects don't respond to the global sea level rise. They're going to be faced with suffering the relative sea level rise at that location. Absolutely.
So Scott, should we, from a global strategy point of view, should we raise all our embankments, our bridges, our levees by 2 feet over the next 50 years?
You know, I'm going to leave that to the design engineers, and that I skipped one important thing, and I'm glad you asked that, Jean-Louis, and that is we have this uncertainty. There's a tremendous amount of uncertainty. There's uncertainty in what society's going to do in terms of greenhouse gases, and there's also uncertainty within the model, and that's was the error bars that you were looking at there, the 90% bars. So, but engineers are used to uncertainty. Just because it's uncertain, there's no reason to pick the highest possible value. I mean, I'm looking at a bunch of hydraulic engineers, and you guys admit the truth. You've used the C as a Q is equal to CIA, and you've always all used Manning-Zan. You probably did it last week. And you know Manning-Zan isn't right. There's a lot of uncertainty. is it this number, is it that number, and you pull out the Venti Chow and you look at the pictures, or you're just used to it and you got, okay, it's concrete, it's this. But you know it's not that. And so when you get done with your calculation and you're making a design decision, you make a design decision based on the uncertainty. So if you come up with an 18.7-inch culvert, you make it a 2-foot culvert, or wider if it's a fish passage issue. So that leaves, being aware of the uncertainty shown on those graphs I showed, and allowing the design engineer to make the design decisions.
Is there any consideration to consider riverine and coastal combinations? I mean, we usually have riverine separate and coastal separate. We never have them combined together.
Did somebody plant that question there? Yeah, that's always the issue. It is always the issue. What do we do in those situations? And every state has faced it, where you have a hurricane. Texas just had it, North Carolina had it a few years ago in spades, where the hurricane is out there, but it's a 15-year, 20-year event. And the rainfall from the hurricane might be a 50-year event, but somehow they combine in the bad tailwater, and they get a 500-year flood in the median. So we will be addressing that. Yeah, thank you. And I think the tools now are a little unclear. You run both sets of models, and you have to work at it. In fact, the primer talks a little bit about that now. One of the primer that I mentioned talks about, for scour, well, for water surface elevation, sometimes the coastal controls at a location, and yet for scour, you get higher velocities on the riverine, the corresponding riverine storm. Higher, so.
Scott, one more question.
Carl.
The southern transport, how robust is that going to be in the way of skyline? Meaning, are we looking at it from a regional standpoint for all the influences that could, like, say, if it's a bridge? So you've got riverine transport, you've got shoreline transport. Are we looking at that, say some community comes in, or goes on to Florida in case, and does a beach nourishment job, and knowing that, we saw that earlier in Corvallis Beach where, they did this nice job and all that sediment went somewhere. I mean, are we looking at that in terms of the overall?
Yeah, I think we'll put more tools in there related to beach nourishment and dunes, and there are guidance tools for dunes, how thick you make it, how wide you make it to survive a storm. And the problem with that part of Florida, and everybody knew it, if you run those models, yeah, the house falls in the ocean. Well, the house fell in the ocean, duh. So if you, not that you can't use beach nourishment as a solution, it's just got to be done well. Yeah. There's a question back behind you?
Yes, I'm actually a climate scientist, so
Okay.
this is very interesting.
Uh-oh.
And so I think a recommendation I have as a climate scientist coming into something very different and very applied is that we're very siloed in our techniques and codes. And I don't know if you have a recommendation about trying to break down the silos and trying to really think about these multidisciplinary type problems where you're talking about extreme weather and possible changes in climate, sea level rise, and really trying to break down those silos where we actually bring in the scientists to think about these problems and address local issues. I don't know what you're feeling with as far as recommendations on this side.
Well, you're sitting right in front of the guy who's leading NCHRP 1561. Do you know Roger? In that that study, we did do just that. He has the climate scientists on the panel with us, and we are discussing it robustly. Put it that way. That's a good point.
And to add to that, our document HEC 17, which came out about 2 years ago, in our framework, we actually talk about how the climate scientists and the climate modelers are an integral part of the more complex frameworks that you might have for certain types of situations and projects. So again, we recognize, there's a difference between maybe designing a culvert, the size of the culvert versus sizing an interstate bridge like Tappan Zee or something like that, $4.2 billion, $1 billion project, so that we are saying, there's a time where the state DOT should be going to multidisciplinary and including the climate scientists and climate modelers as part of how you approach any given type of project. So I wasn't asked to stand up, but I did anyway, Scott. So.
All right, thank you, Scott.
Thank you.
So, if you're interested as far as the climate, this afternoon, in the same room at around 3 o'clock, we're having another session on climate and kind of the inland hydrology, and Roger will be presenting, and some other folks, perhaps our climate modeler will be presenting as well, so stay tuned. Thank you, everybody.